Hello everyone. Welcome back to my channel Learning Physics with Bhavya ma'am. I'm Bhavya. Today we are going to learn electric field lines. In last video, I explained how to find electric field or what is electric field. Today we are going to learn electric field lines. What is electric field lines? Electric field line is a visual representation of an electric field. By drawing some picture, we are representing how the electric field looks around the charged particle. So that's why it is called as pictorial representation of an electric field. An electric field line is an imaginary path along which unit positive test charge tends to move. This path may be either straight or it may be curved. So if here there is one positive charge, if the source charge is positive, the space around the source charge is called as electric field. This space is called as electric field. Within this space or region, if you place another charge, that charge is also positive. Okay, what is this charge called as? This test charge is called as, this is called as test charge. Okay, this is a test charge. What is this called as? Source charge. So this test charge experiences force of repulsion because both are like charges, right? So this test charge tends to move away from the source charge because both are like charges, right? So wherever you place a test charge, it experiences force of repulsion, right? So it experiences force of repulsion. So this is a direction along which force acts, and we know that along same direction electric field is also acting. Electric field also acts along same direction. Okay. Why? Because electric field is nothing but force experienced by test charge. Okay. Force experienced by unit positive test charge placed at that point. So that's why electric field and force are along same direction. If the charge is positive, field and force are acting along same direction. Okay. So that's why these are the, this line is called as electric field line, or it is also called as line of force. This line is also called as lines of force because this is a line because of force. If the source is negative, this test charge attracted towards the source charge. If you keep a test charge here and if the source charge is negative, then what happens? Test charge is attracted by this negative source charge. So then you would have draw the lines in this direction, right? So line of force is acting in this direction towards the negative charge. That's why this line is called as either field lines or it is also called as line of force. This is just an imaginary line, okay? Imaginary line along which positive test charge tends to move. Is this clear? If the source charge is single, okay, if you place a positive test charge, the line of force is away from the positive charge. If the charge is negative, then line of force or field lines are towards it. So it may be either straight if the source is single, or it may be curved if there are two or more than two charges. Okay, then the imaginary path is curved. Is it clear, student? Now let us move. Now let us learn what are the properties of electric field lines. The first property is, already I mentioned, electric field lines starts from positive charge. That is because here you have to place one. You just imagine you have placed one positive test charge here. So then in which direction it moves? It always moves away from the source charge, right? Because of repulsion, positive test charge moves away from the source charge. Wherever you keep a test charge, it tends to move away from the source charge. That's why it always starts, electric field line starts from positive charge. Similarly, if you keep a negative source charge, then test charge is attracted towards the negative charge. That's why how the electric field lines looks like. See, it always tends towards the test charge tends to move towards the negative charge. That's why field lines are acting towards the negative charge. So if you look at these two electric field lines of positive and negative charge, so you are observing that field lines are radially outward in positive charge. So imagine radius here. Okay, so it is radially outward, right? Along the radius, see, radially outward. Similarly here, it is radially in negative charge. Electric field lines are radially inward. Is this clear, student? So field line starts from positive charge and ends on negative charge. Okay. The second property is electric field lines are continuous curve. Okay. If there are two charges, then it is a curved line. Electric field line is a curved line because it starts from positive and it is going towards the negative. As it goes, as it starts moving from positive charge, instead of going straight, it will bend like this. Why? Because it is attracted towards the negative charge. So here positive charge is moving straight. It is repelled by the positive source charge. But as this is moving, it is attracted towards the negative. Right? That's why you are observing that the route followed by the positive test charge is curved. Okay, the route of or path along which positive test charge is moving is curved. Though it is a curve, even if it is a continuous curve, they do not form closed loop. Why? Why? Because see here the test charge is moving from positive towards the negative. That's why the path is like this, right? But it never comes back to positive, right? The test charge is never coming back to positive. If it comes back to positive, then the route would have been near closed loop, right? So the route would be closed loop. But since it is not moving back to positive, it is not a closed loop. So you are observing that the field lines are just moving from positive ending on negative. Here also it is moving from positive ending on negative, right? So it is not coming back to positive charge. Is it clear? The next point is, if the field lines are curved, then what is the direction of electric field? How to identify the direction of electric field? To identify the direction of electric field, at each and every point, you draw a tangential line. At what point you have to find the direction of electric field? At that point, you draw one tangential line. You know that tangent touches the curve at a single point, right? Draw a tangential line and put an arrow mark along the direction of electric field lines. Okay, so this is a line of force and this is a tangential line. Put arrow mark like this. So this tangential line shows the direction of electric field. Okay, now the next point is electric field lines are always normal to the surface of conductor. It is always normal. So whatever may be the shape of the surface, electric field lines are always normal to the surface of conductor. Suppose if it is not normal and it is acting something like this, okay? Electric field line is acting like this. Then we can divide this into two parts, okay? One is horizontal part, another one is vertical part. I'll resolve this into two components, okay? What is this component called as horizontal component or parallel component? See, this line is parallel to the surface, right? and this component is called as vertical component or normal. This line is normal or perpendicular to the surface. So if electric field line is not acting in, see, if the electric field line is something like this, if it is not, if the field line is acting like this, then we can divide into two components. Okay, is it clear, student? Now, so one component is parallel to the surface, another component is perpendicular to the surface. Suppose if the field line is parallel to the component, then what happens? We know that here there are charges, right? We know that charges are always remains on the surface. Here there is a charges, right? There is one charge here. So there are some charges placed on the surface because this is a charged conductor, right? Charges are always remains on the surface. Suppose there is an electric field acting along the surface, okay? It is parallel to the surface. Then what happens? We know that charge always experiences force along the direction of electric field. What is the force experienced by charged particle? It is equal to Q into Q into E, right? This is a force. So charge, this charge experiences force Q into E. So that therefore these particle experiences force along the direction of electric field and it tends to move along this direction. So this charge moves on the surface. But it should not be happen, right? Because here we are studying about electrostatics. In electrostatics, charges are always remains on the surface of conductor. Charges should be at static position, right? Charges should be at rest on the surface. It should not move. Suppose if the electric field is acting on along the surface, parallel to the surface, then charge would have traveled like this. Charge would have traveled along the surface and moving charges produces current. Moving, there is, if there is a movement of charge, mean if the flow of charge constituted current, there would have current, right? But here we are talking about electrostatics. That's why this should not be happen, right? That's why electric field line should not be along the surface or it should not be parallel to the surface. Then what is the next possibility? This is a next possibility. Electric field line should be always parallel. Electric field line should be perpendicular to the surface. It should be normal to the surface. Electric field line should be normal. Electric field lines are always normal to the surface of conductor. Is this clear, student? Electric field line should not be parallel. If it is parallel, then charge would starts to flow through the conductor, surface of the conductor, and hence it produces current, which should not be happen. That's why it should be always perpendicular to the conductor. Now, the next point is electric field lines do not intersect each other. Okay, so whatever may be the number of field lines, the field lines are always like this. So even if it is very close to each other, field lines are do not intersect. It should not intersect on each other. Okay, suppose if two field lines cross each other, so here you can observe that 1 and 2, these two field lines cross each other. Then what happens? At the point of intersection, if you draw a tangential line, you can draw two tangential line at a time, right? You know that tangential line shows a direction of electric field. And we know that electric field line is a direction along which test charge moves, right? Now, at the point of intersection, there are two direction of tangential. See, there are two direction of electric field, which is not possible, right? At a time, test charge cannot move to two paths, right? Test charge cannot move in two paths. That's why two electric field lines do not intersect. Okay, it should not intersect. Is this clear? Suppose if it intersect, what happens? At the point of intersection, there are two direction of electric field, which is not possible, right? simultaneously positive test charge cannot move in these two directions, right? That's why electric field lines do not intersect. Okay. Now, the next property is electric field lines do not pass through the conductor. Okay, that is because, see, we know that electric field lines are always perpendicular to the surface. See, inside this conductor, charge is zero, right? There is no charge inside the conductor. And hence there is no electric field. There is no electric field inside the conductor. So therefore, there is no field lines. Field lines are not moving through the conductor. Okay, there is no field lines inside the conductor because electric field inside the conductor is zero. Charge is zero, electric field is also zero, and hence electric field lines do not pass through the conductor. It is always perpendicular to the surface of the conductor, right? Now, the next point is electric field lines are crowded means there the field is stronger. Okay, if the field lines are more in number, then electric field is stronger at that region. You look at these three pictures. So in A, some field lines are drawn and there is a lot of space between the field lines, right? So if you look at this picture B, so here compared to A, field lines are more in number. That means compared to A, in electric field is more in B. Okay, electric field is stronger in B compared to A. Okay, because number of field lines are more. But if you compare to B with C, number of field lines are crowded in C, right? So more number of field lines are there. If the field lines are closely spaced, okay, if they are crowded, then electric field is more here. So electric field is stronger if the field lines are crowded. Is it clear, student? So therefore, electric field and electric field is directly proportional to number of field lines. Okay, it directly proportional to number of field lines. Number of field lines. Okay, more the number of field lines, stronger the given field is. Okay, or if the field lines are denser or it is closer to each other, closer or denser, then field is stronger at that region. So electric field is directly proportional to number of field lines. And one more thing is electric field is directly proportional to magnitude of charge, right? So therefore, if electric field is stronger means more charge is more in number. Okay, magnitude of charge is more. Okay, if the charge is more, then electric field is stronger. And by looking at the field lines, how you'll come to know that electric field is stronger? If the field lines are more in number, okay, if the field lines are denser, then you'll come to know that electric field is stronger at that region. Okay, so therefore compared to A, B, C, so here C is having more number of field lines, therefore electric field is stronger in around the C. Okay, so now electric field lines contract longitudinally. Longitudinally means lengthwise because of attraction between unlike charges. Okay, so this is a sketch of electric field lines due to dipoles. This is one of the important sketch, students. Please remember this, practice this. This is asked for 2 marks in board paper. Okay, sketch electric field lines in case of dipole. So here I am having one positive charge and here there is a negative charge. We know that electric field lines always starts from positive charge and moving towards the negative charge. It ends on negative charge. So suppose if there is only single charge positive, then electric field lines are straight line, right? Because of second charge, that is negative charge, these field lines are curved. That is because you imagine one test charge here, okay, closer to the positive charge. Test charge is repelled by the positive and hence it moves away from the positive. As it is moving like this, as it is moving, it experiences force of attraction. Okay, so that's why instead of going straight, it bends towards the negative charge. Okay, positive test charge bends towards the negative charge. So this is a path along which test charge moves in the space. Okay, so when dipole is placed like this, then electric field lines are a curved line, starts from positive charge and ends on negative charge. You can draw any number of field lines, but see that two lines are never intersect each other. Okay, they should not intersect on each other. And one more thing is, field lines are not a continuous closed loop. Okay, it is not a closed loop. So while putting arrow mark, be careful. So it always starts from positive charge. Put arrow mark like this, starts from positive charge and ends on negative charge. Please don't put arrow mark in this direction, negative to positive. Okay. And you are observing here that these electric field lines are contract longitudinally. Lengthwise it contracts, right? Because of attraction between two charges, it is contract. So here, suppose if there is a positive here, then what happens? Let us observe that in next. So here, electric field lines expand laterally because of repulsion between like charges. See here you are observing that field lines are spread out, right? It is expanding laterally, right? Laterally means sideways. You are observing that here it is expanding sideways, right? We consider two like charges and both are equal in number, right? These two charges are equal or similar, like charges. Then what happens? Imagine here there is one test charge. Okay, positive test charge is repelled by the positive and hence it moves straight. But when it is moving like this, as it is moved straight, it experiences one more repulsion due to second charge. Okay, there is a repulsion due to second charge. That's why instead of going straight, it this positive test charge bends like this. Okay, instead of moving straight, it would bend like this. That's why wherever you want to observe the direction of electric field line, imagine one test charge. Okay, so the test charge is going away from the positive charge because of repulsion, and as it is going like this, it experiences another repulsion because of second charge. That's why you are observing that here the field lines are curved line. Okay, so here field lines are curved and almost here you are observing that field lines are straight. Okay, so because the effect of the force due to second charge is almost less. Okay, effect of force due to second charge is almost less compared to here, right? So here what happens, the positive test charge experiences two forces, one is due to this, another one is due to this. So that's why the field lines are curved. But if I consider either side, see here what happens, it is almost straight line, right? Straight line, because see the force of this one is dominating more than force due to second charge. So because of this, it repel, as it is repelling like this, here there is one more force, but the effect of this is less somewhere here, right? Is it clear, student? Okay, now see this point is called as, the center point is called as null point. Here at this point, so there is no electric field. Okay, so that's why we are not drawing any field lines. Exactly at the center, this line, this middle point is called as null point. Here there is no field line because electric field is zero. Okay, electric field is zero at this point. What is that point called as? Null point. Okay, if these two charges are equal in number and both are like charges, right? Then null point is exactly midpoint, midway between these two charges. What is null point? Null point is a point at which total electric field is zero. Total electric field is zero. Why? Because see here what happens at this point, say this charge, due to this charge, positive test charge experience force in this direction and electric field is acting in this direction. Okay, electric field E1 is acting in this direction. This is E1. Okay, due to this charge, due to second charge, what is the direction of electric field? Once again, it is acting away from it, right? So let me call it as E2. E2. Okay, this is E2. Now this is E2. Okay, now so at this point, what happens? E1 and E2 both are equal, right? Because how to calculate E1 and E2? We know that E1 electric field is directly proportional to charge and inversely proportional to the square of the distance. Since this point is midpoint, so the distance of the charge is, distance between these 2 points is same, right? In both the cases, distance is same and charge is also same, therefore electric field is same. So E1 and E2 are equal in magnitude and acts in opposite direction, therefore what is the total electric field? Net electric field at this point is zero. That's why this point is called as null point. Null point is exactly at the center, so therefore here you are not drawing any field lines. There is no field line at this point, so this is called as null point. If so, this is a null point. Okay, so what is this point? Middle point is called as null point. If q1 and q2 are equal in magnitude, null point is exactly at the center, because see the point midpoint is at equidistance from both the charges, right? Suppose if these two are like charges but they are not equal, let us assume that q1 is more than q2. Okay, then since q1 is more than q2, then what happens? So electric field is unequal, right? Electric field is not equal. So therefore null point shifts towards the smaller charge. So this point shifts towards the smaller charge. Once again, we need to calculate null point. How to calculate null point? What is null point? Null point means where electric field is zero. How to calculate electric field? It is a difference between electric, see how to calculate electric field? It is a difference between two, right? So this here at this point there are two electric field. One is due to q1, another one is due to q2. As I mentioned in previous, electric field is acting in opposite direction. Then what is the total electric field at this point? So total electric field should be zero, means only the possibilities they must be equal, right? They must be equal, then only we will get zero, right? When it will be equal, see here we know that charges are not equal. If charges are not equal means distance should not be equal, right? Distance should not be equal. So but E1 must be equal to E2. E1 must be equal to E2. We know that E is uh, directly proportional to charge and it is inversely proportional to distance. Therefore, E should be equal means here, since charge is not equal, see, if greater the charge means the distance must be greater, so that ratio remains same. Is it clear, student? Greater the charge, greater is the distance. So ratio is remains same. Therefore, E1 and E2 are equal means here Q1 by R1 must be equal to Q2 by R2. Is it clear, student? Q1 by this distance, let it be R1. That should be equal to Q2 by R2. So therefore, if Q1 is more means R1 must be more. Okay, the distance, this distance must be more. Or Q2 is smaller means the distance of the null point from the charge, this distance must be small. That means this point should be closer to the smaller charge. Okay, so therefore this point, null point is closer to the smaller charge. This is one of the important point you have to remember in competitive exams. Okay, null point shifts towards the smaller charge if they are unequal. Is it clear, student? I hope you understand all the properties of electric field lines. If you like my videos, please like, share and subscribe my channel. Thanks for watching.